there is a prefix that starts with an S that ends in me somewhere. Of course, I don't have a link because it's in the middle of an edge, but something like that exists. So I can put some sort of a flag there to denote it, which is what he's going to do, in fact. But at the moment, we know that there's no link. However, there's a crucial lemma that we need to prove first before we tie in this last element. And that lemma is crucial for our time, because eventually this thing needs to be linear. So you need to know that you don't go up n, and then go up n, and then go up n, and then go up n, and you do that n times, so your n squared work. So what you want to do is know that if you went up, so because how are we going to build it? Okay, how are we going to? How does it look like we're going to build the tree? We're going to go up somewhere, climb, and then add something. And then we need to go up again, maybe, and then add something. And go up again, and then add something. So what we want to do is make sure that the height of this and the height of that are roughly the same. That this cannot be a whole lot lower, because if what I had was I climb all the way up here and I go down here, then I climb all the way up here and I go down there, then I climb all the way up here and go down here, that's what means I climb up too much. Instead, what I want to do is to have a situation where if I climb up here, I go up. And then if I climb up here, I go up again. At that point, every time that you climb up, the next time you can't climb up more. So what you have climbed up the next time and the next time, you paid for when you went down here already at the building part. So that's the idea of where our linear time is going to come from, and that's why we need this particular lemma. So let's look at it. This is the crucial lemma, not for the algorithm, because the algorithm is already, you probably almost have it now in your mind, and it's a very simple one. You climb up until you see the suffix link, you go on the suffix link and you add, and there are going to be these flags there that tell you where to break the edge. Okay, so that's the algorithm. The problem is, how do we know that that's linear time? Now comes the lemma. And so what this lemma says is that if AU ends in a node in TI, well, okay, it doesn't matter so much, because the only new AU in TI that isn't in I+1 is this SI. So you need to write it in order to be correct, but forget it. You can consider it the same tree. It's really easy. Then U, meaning AU is a suffix, this is a substring. This is the alphabet letter. So we have an alphabet letter and a substring, and that ends in a node. Well, then U itself, without this, also ends in a node in, well, TI+1, but again, think of it as the same tree. Okay, so if that is the case, then in particular, the depth of x prime has to be greater than the depth of SI x prime. Why? Let's look at the picture again before we prove that lemma. Okay, so here is this picture. So the depth of the lemma is saying that if AU ends in a node, then U ends in a node, which means any SI, this really starts with S. So any SI something that ends in a node, whatever the something is after the SI is going to be ending in a node here also, which means that for all these nodes, every node here has a corresponding node here on this side. And here there may be more nodes than here. So what it means is that the depth, that if I go up from here to here, there are more nodes here than here. So I'm actually going up in the tree rather than down. Okay, the number of nodes is how far am I in the tree. That's where my walking is. So that's why this lemma is going to really prove the property that we want, and that is that x prime is actually lower down than SI x prime, because every node that you have here you have a corresponding node here. Okay? Now, the proof again is a simple thing when you breathe and wake up and go to sleep and breathe suffix trees. So the proof comes natural, but let's see. Suppose that AU ends in a leaf. A leaf is a node. What does it mean that AU ends in a leaf? It means that really there is some suffix A followed by the substring U followed by $1. That exactly means that it's in a leaf. But if there is such a suffix, then isn't there also a suffix U followed by $1? I mean, obviously, it's just, well, if A something is a suffix, throwing the A, whatever is left is a suffix. It's the next one on line. So obviously, if AU ends in a leaf, then U ends in a leaf. That's clear. Okay, but if AU ends in an internal node, what does it mean? So that's when we started out the class and I showed some of those examples. What it means is that there is somewhere on the string where there is an AUB and somewhere else where there is an AUC, where B is not equal to C. That's why AU ends up in a node. So let's draw this. So we have our string, and somewhere we have A, U, and C. Somewhere else we have A, U, and what did we call it? B. So when we were looking for this suffix in the suffix tree that starts by A, U, it gets to some point and there's a C, and then this suffix, it starts by AU and gets to some point, and that's the B. Okay, so this was the situation in the suffix tree. It means this was the situation in the text. Okay? Now, consider now this suffix and this suffix. So they're going to start here somewhere, and you have U. But that means that at some point, you have this suffix, and you have to go to a C. And at some point you have this suffix and you need to go to a B. So obviously, if you have an AUC and an AUB, then you have a UC and a UB somewhere. And this is, in fact, also the intuition behind the lemma. I mean, when you add this, you're giving yourself less options than when you don't. Because it could be that somewhere else we had BUD also, but we don't have AUD. Okay, so you're giving yourself less options by adding this A than by throwing it out. And that's why on the path of AU, there are going to be less nodes than on the path of U. Because the path of U also started by other things, and so there could have been other things happening in the string, whereas AU was less cases. And so that's the end of the lemma, and that also proves the height property that we were interested in. So now we have all we need. All we need to do now is put in the flags, the pointers, show how we maintain them, and then plug in the time the time analysis. So what do we need? What do we need? For every node U and every sigma, we need a flag that indicates if sigma U is in T implicitly. And we already said that obviously this has to be a node. So we have the flag. And we have the pointer. This is what is also called the suffix link. We have the pointer to the node where sigma U ends if it appears explicitly. The notation of what?
So when you're having the node U, when you're talking about...
Well, U is... Yeah, okay. So when I say a node U, I mean the node where the path U ends. Okay, yes, I should have said that. I think it was even written somewhere. because when I write I try to be more explicit than when I talk. But yes. So when I say a node U, I mean, it's a good point. I should have said that before. When I say a node U, I mean the node where the substring, the path that has U on it ends. That will be the node U. Let's see. Let's see if I was senile or I said that somewhere. Okay. So yeah, it was in a little. It was in a little font and it was in parentheses, and I didn't say it. But we will say that something is a node and mean ends in a node. So that some string is a node, we mean ends in a node. Okay? Yeah. Thanks for keeping me honest. Okay, so we have these flags and pointers, and so our algorithm is going to say the following. We added si plus 1 to the tree. Good. So run up the path until you find the si flag. When you find the si flag, you know, oh, okay, this is it. Si of Si obviously was the next letter. Okay, you read the next letter, you see that it's Si. The next letter that comes from the text as it's going from N towards the 1. So you read the next letter, you know that it's Si. You run up the path, and all of a sudden, you encounter the Si flag, so you say, okay, this is it. That's the head. Okay, but what's the length of the head? That I don't know yet. So you keep running up the path until you find the pointer, the suffix link. So you keep running up, and as you run up, keep track of the differences between flag and pointer, because as you run up, you know the length of the string on every edge, because it's actually written there. In fact, that's what's written. You have a pointer and a length, for example. So you have a pointer to the real text, and the length of how much of that appears in this edge. So add them up until you get to the pointer, and you know this is the length that we're going to need to cut on the edge on the other side when we cut it. So you keep running up until you encounter the Si pointer. When you get the pointer, you jump to SIX prime. So you jump to SIX prime, and you know, okay, now here is the edge that I need to cut, and I also even know, because I kept count of the difference between the flag and the pointer of the length. So I even know that edge, when I cut it, where I cut it. What's the length that I cut? Well, how much is here and how much remained there? And at that point I also know, once I cut it, I add a new node, and then add to the other side the continuation of the or add that suffix. So the pointer to the suffix that you need to add. Okay, so the work is clear, but that's one step. And in order to prepare your data structure for the next step, you need to now update all the pointers and all the flags, so that when the next one comes around, they don't flounder like a fish out of water. So let's see. I think I need this to be a little bit smaller. Good. Okay. So the picture here looks very good. We need to update the flags that change because head and SI are introduced, and we need to update the pointers that changed because of the new head and SI. So two things happened, and the two things are, we have new nodes. These new nodes, they need their flags and pointers, but we also need to fix all the flags and pointers that changed because of these new nodes. So they have theirs, and we need to change the tree to reflect whatever was added. Okay, so let's think a bit. Because this is what was added, SI plus 1, it means that SI plus 1 now has a pointer. That's a suffix link. It now has a pointer that points straight to here. Right? Because that is exactly what was added. So we now have a pointer. Now, X before was a flag, right? Because that's where we broke. But now because we broke it, this flag is going to become a pointer again. So X itself is now going to get an SI suffix link to the new node that was introduced. So the new nodes that were introduced, this guy points to it, and this guy points to it. Now, all of the nodes between X and X prime used to have SI flags, and they continue to have SI flags because they all appear somewhere here on this edge. And X prime had a pointer, and it continues to have a pointer because the node did not disappear. There was a pointer, the node is there, so the pointer stays. However, we're going to need new flags in the entire path from SI plus 1 to X, because this entire edge is SI followed by these guys. So all the nodes from here to here are going to have SI flags. Okay, is it clear why they all get the SI flags? If something is not clear, yell. Or you don't need to yell. I mean, let's not be melodramatic, but just raise your hand and say, can you please explain it in a better way? Okay, so I explained it in a good way already. Fine. This is one thing that I've actually learned when I said the better way. Sometimes a student would say, can you repeat that? And I say, no, there's no point in repeating it. You didn't understand it the first time. If I repeat it, why are you going to understand it again? I need to explain it differently the second time. So perhaps what confused you the first time is not going to confuse you the second time. That's why I didn't say that you should say, can you repeat it? Because that's useless. But can you explain it better? That would be the way to go. Okay, now, one more thing that we need to... So this fixes everything that points to these guys. Now, the only other thing that we need to do... Now, there's no one else actually that would need to have suffix links pointing to it, because this is where this path, but without the SI is. So those are the only places that actually point to it. So there's nowhere else in the tree that would need to have their trees or flags changed, because nobody else even cares about what's going on in this godforsaken little path. So, but the only thing that we're going to need to do is look at the flags and pointers here and here. And so, obviously, there's no flag and pointer from anywhere here, because this guy is the longest. So there's nothing here, and we don't need to do anything. There will be, in fact, once we add the next suffix, so he is going to get the pointer, but right now there isn't. And he is basically going to inherit all the flags and pointers that were here, because anything that had a flag or pointer here is going to have a flag and pointer there, but no pointers. Why no pointers? Because again, it didn't exist before. So it cannot have a pointer to something, because that would mean that there is something that is of a lower resolution, as it were, that splits, and he himself didn't. So that can't be. Therefore, pointers it doesn't have, but all the flags that were in the node below it, and all the pointers that were at the node below it, they're all going to imply that he gets flags. So he's just going to copy all the flags and pointers from his child, and that fixes everything for the next step. So we have the details written here. Everything that we said and showed it in the picture. We set all the SI flags all the way from SI plus 1 to X, because that's the part of the new edge that was added. SI plus 1 points to SI plus 1, which is SI. X is going to point to SIX, which is the head, because we broke it there. And SI is the longest substring, so no flags or pointers. And if the head was already a node, then we're really done. Because it could be that we didn't break anything. It could be that the flag and the first thing we reached wasn't a flag, but the pointer itself. That can happen as well. At that point, we're done. But if not, if it's new, then every flag and pointer in the node below it is going to set an appropriate flag in head, and again, no pointers, and there is an explanation of what we said here in parentheses, because a pointer would mean that actually there is a break, but there wasn't a break. So, in the case where the head was empty, then it's easy because you just update you just add flags all the way to the top. Now, notice that adding all these flags is really a lot of work, but it's a constant amount of work to the running up that we did to find the original flag. So it doesn't matter how many times we run on how many constant times we run on that particular path that we already ran. So we run up, and you can, as you run up, already do the updating of the flags and everything, because you know that that's what's going to happen. But the time is going to be counted by the running ups. You always have to count how much we ran up, how much we ran up, and how much we ran up. And the point is, as we said, when you run up and you go over, the next time that you're going to run up, you're going to run up less, because you're not, you can't be lower. However, you may be one lower. Why? Because it could be that, in fact, you were at the same height as before, and now that you broke an edge, you added one to the height. Otherwise, you have no place. Okay, so whenever you amortize, as you know, there is some place where you pay and some place where you gain. Where do you pay? I mean, here you only gain. You go up and less, but how did I go down? Well, that's how you go down, because it could very well be that when you broke it and you added, you went down one step, one level. And that's where you add. But the point is that you can only go down, the levels that you can go down is n. So you go up and down more or less at the same height. We're going to look at the formula in a minute. Okay, so intuitively we already spoke about this time, and we said that at every step of the way, the depth is incremented by at most 1. So whenever we run up a lot, we may only run down 1, so therefore we're going to charge running up a path to the building it down. So the total should be linear, but let's formally see what's happening here. So what we're really doing is the following. The total time is less than or equal to the sum of all these guys. The difference between the depth of Sn plus 1 and Sn plus 1, because the one that we added. So it could be that we added 1. But we add to that the difference between the depth of Sn and Sn minus 1. Okay, because from Sn plus 1, we went to Sn, and then from Sn to Sn minus 1, and so on. Now, this is a telescopic kind of thing. So you're going to minus plus, minus plus, minus plus. So the point is, you add up with this, with the depth of the tree, plus O of n, because the O of n is you add 1 at every, plus O of n, the n was cut here. So you add 1 at the end of every, possibly at the end of every cut, and therefore the depth of the tree, which is maximum n, plus n, your total time is O of n. So that's Wiener's algorithm, and as I said, one looks back and says, why is it that we all thought that it was black magic at the time? And no one said, whoa, how does he do it? How does it work? It's clear when you understand the concepts. All right, so let's go back. Before I go to the LCA, let's go back to the indexing. So Wiener's algorithm we just saw, but we saw a bunch of examples yesterday of how we can use suffix trees and LCAs. Before I get to the algorithm of the lowest common ancestor, I want to do one more example. Okay, Bird and Baker we also saw. Okay, good. So here's where we are. So now I want to talk a little bit about the edit distance. I am still going to be using the lowest common ancestor, whose algorithm we're going to see next. But right now, I want to talk about the edit distance because this was a pretty neat use of suffix trees and LCAs. So as you remember, Galil in the NATO conference came up with 13 open problems in stringology, and one of them was, if I allow myself k, if I only want to find the places where a pattern has k mismatches in the text, no more than k, can I do that in time O of nk? And we saw that with suffix trees and LCAs, the kangaroo method, which so annoyed the NSF guy, we can do that in time O of nk. But the harder question was, what about if you're talking about Levenshtein distance? Levenshtein identified two more edit operations, as we said, insertions and deletions, and we saw the examples. So in fact we say that a pattern matches a text in a particular location I with k edit operation if k is the smallest number of edit operations required to make a pattern match the suffix ending at T1, T2, Ti. And why ending? Because we're going to see that this was done using dynamic programming initially, and now we're going to do this better. Okay. So the idea for the algorithm is really dynamic programming. So let's see the dynamic programming algorithm, whose time is going to be O of nm, and then we'll see how we can change that dynamic programming algorithm to actually go down to O of nk, which is what the great idea here was. So for each I and j, let edit ij be the minimum edit distance of P1 to Pi ending at Tj. Okay, so as every dynamic programming algorithm in the world does, you want to know what is the recurrence relation, as it were. I mean, what is the induction that you build on from the smaller pieces that you already did. So let's assume that we already figured out the edit distance of all the prefixes of the pattern that are less than I, and all the locations in the text that are less than j. In particular, the pattern prefix P1 Pi ending at text location j, we know what is the edit distance of that. But we now need to see what's happening for the next one, I plus 1 and j plus 1. Okay, so let's see. If t j plus 1 is equal to Pi plus 1, then we already know what's the smallest number of changes that we need to make to the pattern in order to match the text here. And if we know that smallest number of changes, since this matches, then obviously there's no smaller number of changes that you can do all the way to the end, all the way to I plus 1 and t plus 1. So edit of ij, I plus 1, j plus 1 is equal to edit of ij. So that case is the easy case. We don't need to dwell on it for too long. But if they're not equal, then that's where we need to stop and think. Because it could be that the edit of I plus 1, j plus 1 is equal to the edit distance of ij plus 1. Because in fact, so this is a mismatch. That adds an error. You look at all of these guys, this is an error. So edit ij plus 1 is going to be the edit of I plus 1, j plus 1. So it could be. On the other hand, because we allow ourselves not just mismatches, so it could be that there was a deletion here. And in fact, edit I, j plus 1 is what I'm looking for. So it could be that if you're looking from here to here, everything matches. And all that there was is really, there was some deletion in the text. So the pi plus 1 should have matched something here that doesn't exist. So that's the error. But the continuation from here and here is going to be all the same. So everything is peachy. So that's what we want. So if that's the case, then edit ij plus 1 would be the way to go, because it would be less than edit ij plus 1. And if that's the case, and really the deletion would explain this situation better, then that's how I should go. So I need to take the minimum of these two. But there's another third option that we should consider before we take the minimum, and that third option is perhaps there was an insertion. In other words, let's look at edit of I plus 1j, because it could be that this, everything is equal, all the way from here to here, and this was just a insertion into the text, but it shouldn't really be there. So again, the continuation here and here is the same, and this is the same, so this is the one single error that there is. So I shouldn't be counting deletions and I shouldn't be counting mismatches. What I really should be counting is this insertion. So these are the options, and nothing else can happen. Thank you. And nothing else can really happen here. But of these options, and again, this is something that we always do in all of these kinds of algorithms, we assume the minimum number of errors happen that could have happened. So we take the minimum. We don't say, well, there really were 3 mismatches rather than 1 insertion. We don't say that. So we assume that if 1 insertion is going to explain it, then that's what happened. Therefore, edit of I plus 1, j plus 1 is going to necessarily be the minimum of all of these 3 options. So that would be the recurrence. And what that means is that now, when we want to write the algorithm itself, it's a very simple filling up of a table. So this would be your entire algorithm. So you're going to take a table, you're going to say, this is the pattern, this is the text. So this is when we said p of 1 through I, it's here, and the text in location j, that would be there. So every such box, ij, means the edit distance of the prefix of length I of the pattern ending at location j of the text. And of course, in all such things, you have to initialize. So we're going to add the 0, because the text can start in the empty text, that's also a substring, and the pattern is an empty substring also. So therefore, the empty substring before the beginning of the column is going to have entirely 0 errors, no matter what place you are, because when you try to put the empty pattern everywhere, it's not going to encounter any errors. Empty is empty. So you start off with initializing a 0 row, and the 0 column is going to be initialized at 1, 2, 3 to m, and that's of course because before the text even started, if you're going to say how many errors do I have that end before the text started with the first pattern position, well, 1 error, because you're trying to stick a letter there and there's nothing there, so obviously there was a deletion, so there's 1 error. But if you're trying to stick into nothing 2 elements, then you have 2 errors. And if you're trying to stick the entire pattern in nothingness, then you have m insertions. So this would be the that would be the initialization of the leftmost row. So that's how we initialize everything. And then we fill it. And the way we fill it, we're going to go from top to bottom, from left to right, row by row, and fill it up this way. So we fill the entire row here, and we fill this row up to here, and now we want to fill this element in this row. And how do we fill it? So exactly what we said. If pi is equal to tj, so we look at pi and tj, and if they're equal, then eij is ei minus 1, j minus 1. Because we look at the edit distance that was here, and there was no error, so we just copy it. So you go 1 over from here, you write down what's there, and that's That's going to be your edit distance. And otherwise, if it's not equal, then there's going to be for sure an error. So it's 1 plus, but an error of what? 1 plus what? The minimum of these guys. The minimum of this guy, and that guy. And those were exactly the three situations that we said before. The situation of the pattern ending in location J, but the position before, the situation of this position of the pattern ending in J minus 1. You look at all of these, take the maximum of them, and take the minimum. Take the minimum of them, add 1, and put it here. And then you move on. So your time is clearly O of nm, because this is an n by m matrix, and you're working exactly O of 1 time in order to fill in every square. So you fill them all up, and when you get to the end, you got yourself the edit distance in every location. So the m in location J is going to be this edit distance. The pattern ending in this location is going to be this edit distance. So you have it in time O of nm. Let's look at an example just for people who've never seen this before. Excuse me. Thank you. Now the throat got lubrication, it can run a little bit longer. Okay, so our text is ABABB. So as we said, we start with 0, but then I wrote, rather than the indices, I wrote the text and the pattern, so it's easy for us to see. So we have ABB, and then the pattern is ABAB, and we want to know what's the edit distance. Now, so the first row, obviously, we said is 0, and here it's 0, 1, 2, 3, 4. That's good. But now we're filling this row, and we're asking ourselves, what do we write here? So the question is, what's the edit distance of A ending with an A? Well, they're equal. So the edit distance should be 0. But according to our algorithm, it's also going to be 0. Because they're equal, we just copy this edit distance here, which was a 0 to begin with, and we copy it over here, and that's it. So it gives us the answer that we wanted, but we also see that mechanically, from the algorithm that we set, this is what comes out. Now when we come to this guy, so here we're saying, at this position, ending here at this AB, so ending here at the text, we have an A. What would be the edit distance? Well, clearly A is not equal to B. So it could be that this was a mismatch. Mismatch means we have to go from here to here. So we look at what would have been the edit distance, the one before this ending here, which was 0, plus a mismatch, that's a 1. Mechanically, it means we're going down from here. But it could be, and that's here, A versus an A. That was the match. But the B is here by mistake, and that's the mistake. So we come from here, and we do a 1. But it could also be that the B should be here, but there should have been an A following that B, and that A got deleted. So in fact, A would have matched the A. So that's where we come up from the top. So the B itself matched the emptiness, and there was an A here, and the A that was here and was thrown out, that's the one that, that's the error that's added. So the one that we get here actually comes from all three possibilities, because it could have been a mismatch, it could have been an insertion, it could have been a deletion. We don't care, because the minimum is the same, and so we do a 1. Now, these arrows that I drew here in blue actually means where you could have come from. So in some places, like here, for example, you can only come from one place. In some places, like here, you could have come from 3 places. What that actually means is that if you really want to write down all the possibilities, you may have an exponential output. Because if you're going to go back and look at all the possible arrows as it splits all the positions where the minimum was the same, you're going to get an exponential blow-up. So obviously, you're probably not going to want to write down all the options. However, implicitly, all the options are written down here. So if somebody says to you, I think that this is how things happen, you can follow the arrows and see whether that's how it happened. So having all the arrows here implicitly gives you all the options, but all these options explicitly would actually be exponential. Okay, so we run through from the top, and here's a place where is interesting, because here we only have 2 arrows. Why did we only have 2 arrows? Well, A is not equal to B. So it could be that we came up from here and it was a mismatch, and it could be that we came up from here because there was an A that was missing at the end, so this B is an insertion. But it couldn't have been a deletion, because a deletion would mean that the A came before the B, but there wasn't an A before the B. So there was already one error here. Therefore, if you add 1, you would end up getting a 2. So the minimum is either this or that. Not all options are good. So as you can see, sometimes there are 3 options, sometimes there are 2 options, and sometimes there's only a single option to get somewhere. And that's here, because when you see an A and an A, then there's nothing else that you look at. A matches an A, and therefore there's 0 errors. You come up from here. All these other sides are not to be considered, because what was before, if you came from here, anywhere that you came, you're going to have to make an addition, and so you're not going to get a 0. So sometimes you have 1, sometimes 2, and sometimes 3. We fill the first row. So let's look at something interesting. Okay, so let's look at here. This we got a 2 here. Why did we have a 2? That's actually mechanically very simple, because it means no matter where you come from, you have to add the 1. But the first question you ask yourself is, why do I need to add the 1? It must be that this is not equal to that, and indeed it's not. So you're saying AB, 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 AB ends here, and you're saying that you have 2 errors. So why do you have 2 errors? So we said, okay, because we came from here. So what does that mean? It means that ABA had 1 error over here, and indeed ABA would fit here with 1 error. And then if you want to then add the A and the B, they don't really match, so you're going to have one more error. And that's where this arrow comes from. What I'm asking myself is, why didn't I put this arrow and this arrow? Because all of these would also have been good, but okay, there should, see, you find, you constantly find new things to change. So if this was in PowerPoint, I would have run in and made the change, and now it's mechanically done, so it's always a problem. You know, the mechanical engineering thing, excuse me, I have to tell you this, because on Saturday I was in Ahmedabad, and I was in some hotel that they had the idea that when you eat breakfast, they don't want you to be bored. So they had these placemats with all kinds of jokes all over. And it wasn't the same joke. So every time that you sat, you had another placemat, there were new jokes to look at. But one of the jokes there said, what's the difference between a mechanical engineer and a civil engineer? And the answer is, a mechanical engineer builds weapons, and a civil engineer builds targets. So that was the joke in Ahmedabad on the thing. They also had another joke with engineers, actually. You know how they say about the difference between the pessimist and an optimist when they look at a glass? So they say, the pessimist says the glass is half empty, the optimist says the glass is half full, and the engineer says the glass is twice as big as it should be. So yeah, they had these jokes. It wasn't so bad. Some jokes were better than others. These were some of the better ones. Okay, so that is the so this is the idea of the dynamic programming algorithm. Now, those of you who have seen this or a similar one, like for the longest common subsequence, has a very similar dynamic programming algorithm, except you take the maximum rather than the minimum. But some of you haven't seen this. If there's any questions, now is the time to ask, because I'm going on now. So the time is O of NN, O of NN. And Galil, when he says, okay, now I only allow you K errors. So if I only allow you K errors, can you do this in time O of NK? Well, the answer is, how can I do that? Now, here comes the beautiful idea that Gadi Landau had. He said, well, let's look at this dynamic programming matrix. And if you say that you only allow up to K errors, and let's say K is equal to 1, so it means that all of these indices you don't want to look at, because this has 2 errors, this has 2 errors, this has 3 errors. So what he said is the following. Let's look at the matrix and see what happens here in a diagonal. When you're going from here and going down the diagonal, you can never have a lower number in the diagonal than the number that you had before. So these numbers are non-decreasing. So here you have 0, 0, 0, then you go to 1, then you go to 2. Here you have 0, 1, 1, 1, 1. And here also 1. Here you have 1, 1, 1, 1. Here you have 2, 2, 2, 3, 3. The numbers only go up. They cannot go down in this dynamic programming matrix. So if the numbers only go up, he says, all right, then let's consider only the diagonals up until we get to the number that we care about. So we want to consider, once a diagonal reaches, so if I want all the locations where I match with edit distance no bigger than K, as long as the numbers, as they go up, as long as they're less than K, let me go down the diagonal. And as soon as the numbers reach K plus 1, stop with that diagonal. Now the number of diagonals obviously is going to be O of N. So if I stop at K, then the number of changes that I get in every diagonal is K changes. So if I can somehow only spend time O of 1 per change, then I should be okay. And somehow do this in time O of NK. Now again, this is like the idea of the tanks being upside down. Because so how do you do that? Because look, I mean here you don't spend time O of 1 until the change. And so why do you assume that you can spend O of 1 time per change and at that point to do well? Okay, so here's the thing. And that's where that is where suffix trees and LCAs come in and help us. So what Gadi Landau did is, in fact, he says, let me do suffix trees and LCAs on the dynamic programming matrix. And so I'm not going to do the dynamic programming the way that you do, but I'm going to do the dynamic programming matrix using suffix trees and LCAs. Now, why can he do that? Because, look, why was it that we had 0, 0, 0 all the way here and then it changes to 1? How can it be that you have on the diagonal 0, 0, 0? When would you have a 0 going down here? Is when they match. So you have A equals A, B equals B, and then A is not equal to B already. So you continue down this diagonal with a 0, 0, 0 as long as they match. But as long as they match, we know how to do that in constant time. Because it's a substring of this and a substring of that, and a substring of the pattern and a substring of the text, And we said that part of the magic of suffix trees and LCAs is that you can tell in time O of 1 how far these two substrings are equal. So you can actually run down until the 1, and then suppose there was a 1, 1, 1, 1, 1 going on. Well, the reason there was a 1, 1, 1 going on a long way is again because there was no change. They were all equal, so there was no reason to change from the diagonal. So again, you're going to do a suffix tree and LCA. So that's the intuition behind it. How it can help you run on the dynamic programming matrix itself, which is a beautiful idea. You say, okay, here I have a dynamic programming matrix. Its size is O of nm, but I'm going to compact the dynamic programming matrix. And so it's going to be smaller, just for what I need, and I'm going to compute things faster. So let's look at a little bit more into the details here. So the dynamic programming matrix, if we look at it, the first row we said is 0. And so my question to you that I asked you before was, which of these diagonals does the 0 go down? And these diagonals are exactly, the 0 is going to go down as long as this is equal to this, and this is equal to this, and this is equal to this, and this is equal to this. Okay, so what you're going to do is take the text and take the pattern, concatenate them, construct the suffix tree, and then do the LCA, and then do the LV. Exactly like all the examples that we saw yesterday. So you start with that. Now, here, what are you saying? You're saying that in position 1 of the text and position 1 of the pattern, you want to know how far this thing is equal. So you do an LCA query of 1 and 1. Here, let me write this. Writing is always better than saying and waving hands. So we took the text, and we took the pattern, and we constructed the suffix tree, and we did LCA preprocessing, and we did a DFS and wrote the level and the level computation. And all that for a fixed alphabet, as we know, took us linear time. Now, we start here and we're asking how low can we advance on this diagonal until there's a change. Well, we're going to inherit what was before, which was a 0, as long as this is equal to that. So what we're going to do is an LCA query between the first position in the text and the first position in the pattern. And we're going to ask, what's the level? If what we get here is 7, then that means that we can go all the way up to 7, and then there's going to be a different value. Now, we do that for every diagonal. So if we're talking about here, we're still looking at P1, but let's say this is index 5 already. So we do LCA of T5 in P1, and we look at the level, and that tells us how much we can advance in each one of those. So at this point now, we have extended all our diagonals as much as we can extend with 0 errors. And we know that already here there's going to be 1, and here there's going to be 1, etc. However, there's something else that happens in this dynamic programming matrix. What happens is that in order to compute whatever was written here, I take the minimum of what was here, and what was on the left. I take the minimum of them and add 1. Okay, so in order to compute this one, I need to know these 3. In this particular case, the diagonal that's under this one, I know that it wasn't a 0 because I went through all the zeros and extended them. So here, this diagonal, it wasn't 0 errors. There's more than 0. But it can't be more than 1 because he inherits the 1 from the top. So all of these guys actually inherit the 1 from the top. And in this diagonal also, it wasn't 0, but they will inherit the 1 from this column that's to their left. Similarly, all of these guys are going to inherit the 1 from the top because this was a 0. 0 plus 1 is 1. So all of them are going to be at most 1. They can't be a 0 because if they were, we would have extended them in the 0 stage. So we know that this is a 1. So in some sense, we have reached a situation where after we're done with the 0 level, we also know already a bunch of 1s that can be extended to a certain location. Because all the 1s that are below or above a 0 diagonal, the 0 diagonal is going to make them a 1. So after stage 0, which was the stage of extending all the diagonals that have 0 errors, we're going to now want to extend all the diagonals that have 1 errors to the maximum range that the 1 can reach. And a good start is, well, we know that the 1 is going to appear at the end of each one of these zeros, obviously, because there's a 0 above it, and the 0 doesn't extend, so there's going to be an error. The error cannot be 0, so it can't be, so 1 is fine. So we know that all these zeros end with 1s, but we also know that there's a whole bunch of other columns that we already know are 1s, and we know where they end. But that is not the limit of the 1s. That is just the beginning of the 1s. Okay, so at this point, all the 1s that we have written down are the ones that we got because of the 0. That is not the limit of the 1s. What's the limit of the 1s? I mean, some of these 1s can be extended. Why can they be extended? Because it could be, okay, so there was 1 error to get all the way up to here, wonderful. But it could be that now, the text, so we have 1 all the way to here that we inherited, but the next one, so the text in this location and the pattern in this location are equal, and they're equal all the way. So then this 1 is going to go zoom all the way as far as it can go. So wherever a 1 column ends as a result of the 0 level, of the 0 stage, suppose it ended not a 1 column but a 1 diagonal. So suppose it ended in column J. So suppose it ended at ij, okay? At ij in the matrix. Then it could be that if we extend from the pattern in position I plus 1 and the text from position j, everything is equal. If p I plus 1 is equal to t j plus 1, then we can extend it. And if pi plus 2 is equal to t j plus 2, then we can extend the 1 even further. So the 1 can be extended. So in fact, it can be it should be extended until finally pi plus k is not equal to pj plus k. So how do we know how far it can be extended? So how far do we extend it? So we do LCA of t, j plus 1, p, I plus 1, and we look at the length of that, and that's how far it can be extended. So in O of 1 time, we know how far we're extending the 1s. So we have all these 1s as a result of the 0 stage. Now we're going to extend all of these 1s in time O of 1 per diagonal. And at this point, we're at the limit of the 1s. So we do, for every diagonal, an LCA query, O of 1 time, and now the 1 can't go any longer. But at this point, we finished now the stage 1, but we have to now set up for stage 2, and the setup is going to be the same, because if the 1 extended all the way here, so it means that the 2 is going to extend the 1 is going to tell the 2 is going to inherit from the 1. So now we also have a bunch of 2s of where we start, and then in order to extend the 2s all the level to the end of them, to the end of where they change to a 3, again we're going to do suffix trees, LCA queries on the suffix tree. And then we know how to extend the 3. We only want up to k errors. So in fact, we're going to extend every diagonal up to k plus 1 jumps, exactly like we did in the kangaroo algorithm. So we're going to extend all of them to k plus 1. And every one that reached by the k plus 1 jump, that reached all the way to the bottom line, there's going to be a match. And any diagonal that after k plus 1 matches we're not at the bottom, k plus 1 of these stages is not at the bottom, there isn't a match. So here we are. The time is O of nk. Now, so this should be clear from an intuitive point of view, but actually Gadi, who is also I think he's also an engineer in his bachelor's, so since he's an engineer at heart, he says, but this is still leaving you way too much to program if you need to implement this, because you're going to need to keep track for every diagonal where I am and so on. So he says, no, I'm going to tell you how you can do a regular dynamic programming algorithm, really a regular one, but on a different kind of dynamic programming. So he actually changes the axes of the dynamic programming matrix to some other axes of another matrix. This is really pretty. So I mean, you don't need it because you can do it yourself. But the way that he implemented it is the following. So he says like this. Well, as far as the diagonals are concerned, okay, so we know what is diagonal D. Diagonal D is all the Dij's, where D is the dynamic programming matrix, is all the Dij's where J minus I is equal to D. So this is going to be diagonal 0, the blue one. This green one is diagonal 1. This is diagonal 2. This is diagonal minus 1, minus 2, minus 3, etc. Okay, so now he gives names to the diagonals. And now, what he says is, this is very pretty. He says, okay, now, let's now look at another value. We'll call it LDE, where LDE is the highest row in diagonal D, where the number of errors is E. Okay, so you can see here how he changes the axes of the dynamic programming matrix. So now it's not by pattern and text. So the axes are not now pattern index and text index, but the axes are diagonal and number of errors. And the value in every one of these LDEs is going to be the lowest, the highest row in the other dynamic programming matrix that you could reach by in this diagonal and this number of errors. Here, let's look at this example and we'll see how pretty this looks. So this is like, what we're doing now is pure engineering, but it's nice, so we may as well enjoy it. So this was our dynamic programming matrix, okay? And our diagonals are, as we said, 0, 1, 2. This is diagonal 0, 1, 2. And minus 1, minus 2, minus 3, minus 4. Okay? So these are the diagonals. Now the other ones don't end in the other diagonals don't end in the last row, so they don't interest us. So we only care about diagonals that end in the last row because that's the number of errors that we're going to allow ourselves. Okay, so the diagonal 0, 1, 2, and then minus 1, minus 2, minus 3, minus 4. Clearly, what you have here is O of n. Now, because the E is going to be the number of errors, then that's the K. So here you are, you have a dynamic programming matrix L, and the coordinates are the diagonal number and the error number, so its size is nk. It's not n times m, it's n times k. So, wonderful. Now, and what did we say is LE, the value of LE? It means if you're in diagonal 0, how far can you go with one error? So in diagonal 0, how far do you go with one error? It's going to be 3. So that's why we have row 3. That's how far you can go with a single error. How far you can go with 2 errors? So that's going to be all the way to row 4. This diagonal is going to go to row 4. So the red here, 0, 1, 2, is the 0, 1, 2 that we have here, and this is row 2, this is row 3, and this is row 4. Similarly, let's look at another example. Take this diagonal 1. So in diagonal 1, the 0 errors is only in row 0, so that's this one. And then one error goes all the way down to 4. So the lowest you can go with one error is going to be 4. So here we have the matrix of the LDE. And now what you need to do is actually fill this matrix in a dynamic programming way. Because if you know how to fill this matrix, then you're done. Because this is the maximum number of errors. You know how far you can go. If you allow yourself 4 errors, you can go down all the way. But if you allow yourself only 1 error, then as far as you can go, anywhere where you went, where you get a 4, it means that you can get down to the bottom with 1 error. Okay. So the algorithm, the dynamic programming algorithm at this point, is going to be doing what we said. So given k errors, you're going to build minus 1, 0, 1, 2 to k, and then minus k all the way to n minus m, because that's the largest diagonal that actually does hit the bottom. And this is the way you initialize it with the number of errors. And then you just have to fill in the boxes. And you're going to fill it from top to bottom, left to right, as we do as we do always in dynamic programming, but the rules are going to be the following rules. So suppose you want to fill in LD plus 1, E plus 1. So what you're going to do is the following. You start with R as the maximum of all the following. And why maximum? Because that's what we said. You want to go down as far as you can in every one of the diagonals. So the maximum is going to be at least one more than row of E minus 1 errors in the Dth diagonal, because we're now in the D plus 1 diagonal, right? So go to the diagonal D and see where you have E minus 1 errors in that diagonal. That's going to give you E errors in diagonal D plus 1. And then you get at least one more than the highest row of E minus 1 errors of the diagonal above, which is D plus 1 is the diagonal above me. So we're now in diagonal DE. So go to the diagonal above, see how much you inherit from it, and add 1, because that's what you inherit from it. And then at least the same row as the highest row of the E minus 1 at the diagonal below. So that's the diagonal D minus 1. So you look at all of these and add 1. That's everything you can inherit. Either in your diagonal you add 1, or the diagonal above, or the diagonal below. You start from these, and that's what you start with. That's the R that you start. The maximum of that, that's how far you can go down. And now, you extend as long as the pattern is equal to text. So that's the extension. So that's what you do with the suffix trees and LCAs. Do that in time O of 1. So you have time O of 1 to look at the one above you, the one to your side, and the one in the diagonal. And then you do an LCA query. And when do you end? Any row where the M is reached is an occurrence. So the time is O of NK because we filled in the dynamic programming matrix. Okay, let's do here it's a good place to do the stop, but okay, so if you want to fill this one, for example, then what you need is what's here, you need what is here, and you need what is here, and it helps you fill this value. Now, what does, so let's say that we are, let's draw LDE. So this is the diagonal, and this is the number of errors. And what we want is DE. So we want to find out how low can I go in diagonal D with E errors. Okay, so let's look at diagonal D with E minus 1 errors. That's going to, so here I have how far I can go in the same diagonal. So here I am in this diagonal. How far can I go in the same diagonal with E minus 1 errors? And plus 1. Because already then I am at the start of the next one. But it could be that I actually inherited a 1 from the diagonal below me. Okay, so this diagonal could have given me 1, so this one. So it may be that we're going this way rather than that way, yes. So this diagonal could have given me as far as I can go. So let's look at what D minus 1 has with with E errors, right? Yeah. So I go here, as far as E had E, no, E minus 1 errors, right? Yes, because we want to see E errors. So let's see how far we went down with E minus 1 errors, and we increase 1 for here. So D minus 1, E minus 1 is this one, and we increase it with 1, and that's what we inherit from him. And the last one that we inherit is from the diagonal. Okay, so yeah, so diagonal D plus 1. So we go from here. So this is, I guess, how we fill it. So diagonal D plus 1, and we see how far it goes, and we inherit from him. So we inherit from him D plus 1. So that's how far we can go, and then we do a LCA in order to see how far we can extend. Yes, so what it means is that we fill this dynamic programming matrix this way. Okay, so this is the Landau-Wishkin algorithm. And as we say, the time is O of nk. This actually proves what I always say. You don't, if I actually just came and I told you, look at the LDEs and that's how you do it, it would have been a lot harder to understand what's going on. But if I actually explained it to you, what's happening on the matrix, the way that we did in the beginning, and at that point I say, all right, now build the matrix, then it's easy to build the matrix and you understand what's going on. That's always the question of the point of view. Sister algorithm. Now, this is not going to be the simplest algorithm that exists, and it's not going to be the first algorithm that exists. It's an algorithm that I personally like. So it's a purely subjective choice. And because today is Teacher's Day, so I'm allowed to teach the algorithm that I like. But I think that there are a number of nice things that one can learn from it, and some very surprising things also. There are some nice algorithmic techniques, and we're going to see them. And there are also some surprising things, because we're going to be looking at 3 different problems in the duration of looking for the algorithm for the lowest common ancestor. We'll actually see 3 problems, and all 3 of them have uses in the world. But at least 2 out of these 3 problems, the lowest common ancestor and the range minimum problem, we're going to see here a solution to both of them simultaneously. In other words, we're going to start out not knowing how to do either of them, and then do special case of one, helping to do special case of other, helping to do the general case of one, helping to do the general case of the other. So this kind of give and take is very nice. It doesn't occur often in algorithms, and because it appears here, I like it. And so I said, let's do it. Why not? I mean, we're getting close to the end here, so we may as well have fun. Okay, so let's start with the other problem that we're going to solve simultaneously with the lowest common ancestor problem, and that's the range minimum problem. So what's the definition? The range minimum problem is one that, by the way, has many other uses in and of itself in pattern matching. We haven't seen any algorithms that made particular use of the range minimum problem, but they actually do exist. And I believe that many algorithms for the range minimum problem in 2 dimensions, for example, and so on, actually appeared in pattern matching conferences, and some of them in general algorithmic conferences, because they do have a lot of use in pattern matching, but you will see in a minute why this is such a useful thing in algorithms in general. So what's the range minimum problem? You have an array of integers, any array of integers. So depending on what your application is, I don't care, but you have an array of integers. You want to preprocess it, and you would like to preprocess it, obviously, in linear time. But after the pre-processing, you would like to be able to answer the following types of queries. When I give you a range in this array, let's say I and j, I want to know what is the index of the smallest number in that range. So, what is the index k such that ak is less than or equal to all the other numbers in the range? So that's actually a very useful thing to do. Let me give you an example here. So suppose A is a bunch of numbers, 17, 1, 7, 613, 365. Let's put a 2 here. Now, so this is index 1, index 2, index 3, index 4, index 5, index 6. Now, the types of queries that we're going to have is let's say 1, 5. So within this range, we want the index, so the index is going to be 2, of the smallest number in the range, and that is going to be 1. Within this range, if the query is going to be 3, 5, the answer we should get is 5, because that's the index of the smallest number in that range. Okay, so whenever you have a use for that kind of a query, and to know that you can actually get that in all of one time. So you don't need to look at your entire substring. You can get the minimum without looking at everything. Linear time pre-processing. Maybe we'll see how fast we go today, so maybe we can see some example of a pattern matching problem where the range minimum is used rather than the LCA. But in a minute we'll see how range minimum actually helps us solve the LCA problem. And in fact, the LCA problem helps us solve the range minimum problem. And so together, we're going to solve both of them. We're going to be following, as I said, the Berkman algorithm. But the range minimum problem in and of itself, already in 1984, Gabau, Bentley, and Cartesian gave a linear time pre-processing algorithm for the problem that in time O of 1 can do the queries. Now, the range minimum problem, if we knew how to do LCAs, we could actually solve the range minimum problem. And how could we do that? We would use the Cartesian tree of A in order to solve the range minimum problem. So what's the Cartesian tree? So here's another thing that we learned at this point. Let me go to the Cartesian tree. The Cartesian tree is the following data structure. A1 to AN is an array of numbers, and you can see already why that connects to the range minimum problems, because you have an array of numbers. But now we want to define the Cartesian tree TA of A. And the Cartesian tree is going to be a binary tree. It's a data structure, it's a binary tree, and it's defined recursively as follows. So let AI be the smallest number in A, and that is going to be the root of the Cartesian tree of A. So that's going to be AI. And recursively we define the left son of AI is the root of the Cartesian tree of A1 through AI minus 1, of everything that's to the left of it. And the right son of AI is the root of the Cartesian tree of everything that's to the right of AI. That gives you a recursive definition, and you got your Cartesian tree. So let's see an example. So this is our A. The smallest number, of course, is 1. So that's the root of the Cartesian tree. Now, we have a left and a right. To the left, what we have to do, the left son of 1, is going to be the root of the Cartesian tree of this part. Now, what's a Cartesian tree of 9, 2, 8, 10? Well, again, recursively, the root of that Cartesian tree is 2, because that's the smallest one. So that would be the son of 1. The root of the Cartesian tree of this side is also 2. So that's the root. That's the son is 2. But we're not done, because if that's the root of the Cartesian tree here, to its left is 9, but that's where the recursion ends because there's no more. To its right is 8, 10. Now 8, 10, what's the Cartesian tree of that? So the root of that is the smallest number, that would be the 8, and then 10 is a child of 8. So at this point we finished the left side. As far as the right is concerned, the root of this Cartesian tree was 2. This Cartesian tree, the root is 3, so that's the right son of 2. And 3 has on one side is empty, on the other side it's 10. So that would be the Cartesian tree to the right of 2. And the Cartesian tree that's left that we need to look at is this, 5, 6, 7. The root of that Cartesian tree is going to be 5, and then it doesn't have anyone on the left, that's empty. But on the right, the root of this Cartesian tree is 6, nothing on its left, but on its right it's 7. So this is the Cartesian tree of the array that we're looking for. Okay, so that's, the definition is recursive, definition is fairly self-contained, and that's the Cartesian tree. Now, we can construct the Cartesian tree by a greedy algorithm, surprisingly enough, because we defined it recursively. But we can construct it by a greedy algorithm from left to right in linear time. And that's what we're going to see now. And it's actually a fairly simple algorithm as well. So let's say that A1 to AN is the array of numbers, and we want to construct the Cartesian tree, TA of A, greedily from left to right, okay? Let's assume that we already have the Cartesian tree of A1 to AI. Okay, so AI is the rightmost element, and we need to now add AI plus 1. The point is, AI plus 1, for all we know, maybe it needs to be stuck somewhere within that Cartesian tree. Now, everybody in that Cartesian tree is to the left of AI plus 1. So in other words, no matter where I plus 1 is, all these guys are going to have to be to its left. But where exactly is it going to be relative to those guys? I mean, if it's smaller than everyone, then the entire thing should be its child. If it's somewhere in between, then it should be added to some Cartesian subtree of what happened there. So here's how we add AI plus 1. So if AI plus 1 is larger than AI, then obviously it's going to be the right son of AI, because AI is going to be, no matter where AI is, but if it's bigger than AI plus 1, then AI plus 1 is its right son. So we add it in and we're done. Otherwise, and again we're going to have an amortized analysis here, otherwise we can't just make it a son of AI, because maybe because AI maybe its son or something. So we have to go up towards the root. And here is the nice thing, but the way we go up is only on the edge. We don't need to actually go in. We go up on the edge of the Cartesian tree that already exists. So we have some sort of an existing Cartesian tree from A1 to AI. And all we need to do is to go up on this edge towards the root in order to know where it is that we add the AI plus 1. So we go up towards the root until either we encounter a smaller number than AI plus 1, or we reach all the way to the root, and AI plus 1 is still smaller than everything else. So these are the two things that can happen as we're going up from AI. And so what we're going to do, depending on where it is that we are in each one of these two cases, is the following. The first case is that we encounter some element x that is smaller than AI plus 1. If x is smaller than AI plus 1, then obviously AI plus 1 has to be to the right of x. So ai plus 1 is going to be the right child of x. However, the problem is that x may have had some right child before. But if x had a right child before, well then x plus 1 must be bigger than that, must be smaller than that right child, because if it was bigger, we would have already put him in there. So if it's smaller, then it means that ai plus 1 is going to be the right child of x, and x's right child is going to be the left child of ai plus 1, and we have inserted it. That will be the first case if we, as we're going up, we found the smaller element. But if we didn't, and we came all the way to the root and we didn't find any smaller element, what it means is that ai plus 1 is even smaller than the root. And if ai plus 1 is even smaller than the root, then it should be the new root. So ai plus 1 is going to be the root of the tree, and the former root is going to be the left son of ai plus 1, and everything else is already a child of the former root. So that is going to be the algorithm that we use. Let's see how it works on an example so you'll realize it. So we start with 9, obviously there's nothing else, so 9 is the Cartesian tree. Now we get a 2. And 2 is smaller than 9, but that's already the root, so 2 is smaller than the root. What did we say if 2 is smaller than the root? That we make 9 the left child of 2. Okay, very good. Now the 8 comes along, and the 8 is bigger than the 2. So since the 2 was smaller, we do know that everything that comes here is going to be part of this Cartesian tree. So the 9 has nothing to do with the 8, of course, but the 2 is smaller, and the 8 is to the right of 2. So what happens? So obviously it should be its child. So we're going to add the 2 as the right child of 9. The 8 as the right child of 2. So now the 10 comes. And 10 is greater than 8. So we're not going to go any further, because 8 is the last thing we have there. 10 is bigger than it. Then according to our laws, the 10 should be the child of 8. Wonderful. But now comes the 1, and that's it. And it screws everything, because 1 is smaller than 10. So obviously, it's not going to be its child. So let's keep going up on the envelope. We'll go up to 8, and we ask whether 1 is greater than or smaller than the 8. Now, notice that we're not, if the 10 had other children here, they don't really concern that 1, because he's on the other side of the 10. So he should not be compared to those guys. It couldn't be that he's on this side of the 10, he's on that side. So anything that 10 had here is irrelevant. The 1 doesn't compare itself. But he should compare itself here, because he is but he is to the right of 8. So therefore, he should be comparing himself to the 8, and he's smaller. Meaning smaller, so he couldn't be the child of 8 either here. So he's smaller than the 10, he's smaller than the 8. That's why he keeps going up. And then he compares himself to the 2. And he's smaller than the 2 also. And now there's nowhere else to go. Because, as we said, there's never one should never compare himself to the left of all these elements that he compares itself to in the envelope, because these guys are on the other side. He's on one side, they're on the other side. He cannot be on that side of the 8. That's why he goes only on this envelope to the root. And once he gets here again, that side has nothing to do with him. He's not on that side, so he doesn't compare to those either. But he is smaller than the root. And being smaller than the root, he's the new root. So this is what must happen. So now we know where the 1 is relative to everybody here. And however they were organized, they remain organized, because that has not changed. So now comes the 5. And according to our rule, the 5 being greater than the 1, that's the easy case. So here's the child here. And now comes the 6. And again, according to our rule, 6 is greater than the 5, so here's his child. And comes the 7, and our rule again. So, wonderful. I mean, and all this is good. So 2. The 2 comes along, and he's smaller than the 7. So it means that we need to go up. And again, you remember that because he's on this side of the 6, he doesn't care about what's on that side of the 6. So the next element to compare himself to is going to be the 5. So he goes up, compares himself to the 5, and he's still small. Then he goes up to compare himself to the 1. But he's bigger than the 1. Okay, so what happens? 2 is smaller than this guy, and this, because he's the son of 1, he's actually the root of the entire Cartesian tree here, meaning he's the smallest of everything between 1 and 2. But 2 is even smaller than that. So obviously all of these guys have to be the children of 2. So we take the 5, and we know that he's the smallest. He becomes the child of 2. The 5 becomes the child of 2, and the 2 is the child of 1. So far we're doing okay. Now the 10 comes along, and the 10 is greater than the 2. So if it's greater than the 2, it becomes its son from here. And now the 3. 10 is greater than 3, so we have to climb up. But 3 is greater than 2. So in fact, 3 should be the son of 2, because he is the smallest element to the right of 2, but on the other hand, we know that 10 was the son of 2. So therefore, we do what our algorithm says to do, and that's the son of 2, and 10 becomes the left son of 3. Because everything to the left of 10, and in fact, everything to the right of 10 we know was bigger than 3, and everything to the left of 10 is between the 10 and the 2, and was also bigger than 10. So therefore, that's our Cartesian tree. So we have a nice greedy algorithm in order to construct it. Obviously, you could have also constructed it recursively, but then to find the smallest element would have cost you to run and check. And here, in some sense, we just take the elements as they come. But the problem is that we need to talk about the time. Okay, so the correctness is clear because this is what we always did. When we got the element, we saw who is relevant to be on his left and who is relevant to be on his right, and we did the appropriate comparison. So the definition of how we put it in already says that it's right. The problem is with the time, because for every element, it's true that once we put it in, it's, yes? What's?
Two elements comes consecutively and they are same.
The same elements. You can consider the same. You can consider the same elements as decide if you want the new one to be called smaller or the old one to be called smaller. It doesn't matter. It's going to work either way. But yes, I assumed here that it's actually smaller. Of course, the algorithm works when there are repetitions of numbers, and whenever there's a repetition, it doesn't really matter how you decide it. You can say always that the new one is considered the smaller of the two or something. Actually, probably you would want to make it a bit larger of the two so it's easier, you know. But yeah, because then you just add it and you're done. Okay, so as far as the algorithm time. So what we know is every element, adding it in is O of 1, because you fix a constant amount of pointers and it's in the tree and you're done. The only problem is the comparisons, because as we climb up, we're comparing ourselves to a lot of numbers and not going in, because if we go in, we're done. But we're not going in. However, and the amortization here is an easy one, because look that, again, who's going to pay for the comparison? So the guy who is paying for the comparison is not the new element who is comparing and moving, but it's the old element, the one who is being compared to, the one that was already in the tree. Because once you're compared to an element, it means that you're going to go up, you're going to stick, and that element now is going to be shoved into the left of something. He's never going to be compared to anyone ever again. He's going to be out of the envelope. So you can only be compared to once. And since there are n elements to begin with, so you can't have, in the overall running of the program, more than O of n comparisons. So O of n comparisons, and every comparison obviously is O of 1, and then sticking it in is O of 1, so you have yourself a nice linear time algorithm for the construction of a Cartesian tree. So this is the Cartesian tree. And how does the Cartesian tree help us use the LCA in order to solve the range minimum problem? Well, think about what we did with the Cartesian tree. We took an array of numbers and we made it into a tree. Now, what happens in that tree? The way that the Cartesian tree is built, who is on top and who is on the bottom? The smaller numbers are on top, the bigger numbers are on the bottom. So in some sense, you already have the intuition that if you do an LCA of two numbers on the Cartesian tree, obviously the lowest common ancestor is going to be smaller than the two of them. But it will need to be smaller than everything in between as well. So let's take a look. Okay, so this was an example. So the range minimum of ij is really going to be the LCA of ij in the Cartesian tree. Okay, so here, let's look at this Cartesian tree and make it smaller and roll up the and move up the So actually yesterday Professor Misra was very curious about the quadratic time moving that I described in the that we have in Bar Ilan University. So she actually had me pull up one of the videos where I'm teaching there, and she realized how long it takes. That it took so long that the way that I would do it there is when I knew that I'm moving up, I would go and push the button and talk and explain things while this thing is moving up in quadratic time. And even then, I generally wouldn't move it up all the way, but as soon as it came up enough that I can write on, I would quickly run and start drawing because my patience gave up. So the problem is that you will find it hard to get to those videos because their titles are all in Hebrew. So if you write Amihood Amir, YouTube or something, you will get only the English lectures. You're not going to get the Hebrew ones. So yeah, you need some external help here in order to get to those. So let's say that I am looking for this and this, and I want the here 6 and 3. And what I want is the range minimum query. So I want the smallest number between 6 and 3. Now, obviously, we see that the smallest number here is a 2. But because of the way that the Cartesian tree is built, then obviously, since this 2 is between the 3 and the 6, and it's smaller than the two of them, then the 3 is going to be on the right side of the 2, and the 6 is going to be on the left side of the 2. Okay, so in the Cartesian tree, one is going to be on one side of the 2 and one is going to be on the other because it's the smallest number that I'm looking for. But in addition to that, there couldn't be, when we're looking for the range minimum query, so we're going to get this 2. But there couldn't be anything smaller than that, because anything smaller than that is going to be above the 2, So it's not going to be the lowest, it's going to be above the 2. So if it's above the 2 here, it means that the 2 is already on its right side, and therefore all of these guys are going to be on its right side as well. And so therefore, once you get to the lowest common ancestor, it's got to be the smallest number that you have in this particular range. Because if there was any other number smaller in that range, it would still be a common ancestor, and it would be even lower. So anything that's actually even smaller is going to have to be in another place. Okay, so the lowest common ancestor gives us the range minimum, and that shows that if we knew how to solve the lowest common ancestor by a linear preprocessing and an O of 1 query time, then we can do a linear preprocessing when we want range minimum, we do a linear preprocessing of the array, we do a linear construction of the Cartesian tree, and we do a linear preprocessing of the LCA, and at that point in time O of 1 we can get LCAs, and that's going to give us the RMQs. So that's one direction. Now let's look at the other direction. So suppose we knew how to do So the other direction is, assuming that we know how to do range minimum, can we then use that to solve LCA? So that's the other side of the coin, and we'll show that we can do that also. And at that point we'll say, okay, so this one can solve that, that one can solve that, but we really don't know how to do either of them. So how do we help each other here? So that's what's going to happen. So given a tree T, and we want to use the range minimum to solve the LCA, well, then obviously, since we're going to use range minimum, then we have to take this tree and somehow make it into an array, because range minimum works on an array, not on a tree. So this is the opposite of what we did before. Before we had an array, and we wanted to use a tree tool in order to answer a question, so we needed to make that array into a tree, where the property that we want on the array is going to translate to the property that we know how to find on the tree. Now here we need to go the other direction, because what we have is a tree. We need to make that tree into an array where the property that we want in the tree is going to be the property on the array. Okay, so we assume that we have a tree. Let's consider the Euler tour of that tree, because the Euler tour of a tree is one easy way of making it into a string. So what's the Euler tour? It's basically all the elements of the tree, as you would get if you do a depth first search on the tree, but you write down every element as you touch it. It's also called sometimes the first visit in a tree. But you're going to actually write down, you go by the first visit order, but you write them all down. So you start from A, and you're doing a DFS. So you write A, you went down to B, you went down to E, you will go up to B, you go up to A, and you write down every one of these as you're there. Then you go down to the C, down to F, up to C again, down to G, up to C again, A, D, H, back up to D, down to I, down to H, and then back up, I, D, and back to A. So that would be the Euler tour of the tree. You do a DFS, and every time that you visit someone, you actually write it down. You now have yourself an array. And this array is not too big either. We want to show that we haven't done here anything more than linear. Obviously we haven't, because look at what happens here. We basically write down every edge twice, because as you go down an edge and up an edge. So every edge is written twice, plus 1, because the last element that you start and end So every edge is written twice plus 1. That's the size of it. And since the number of edges in a tree and the number of nodes in a tree are practically the same, the number of edges is one less than the number of nodes, but that just means that the size that you have is big O of the size of the tree. So you're still a big O of n, you haven't done anything nonlinear. Okay, let's define some definitions here. So let's define LV as the index. Okay, so why am I doing these definitions? Let's again go to the intuitions. Why am I doing these definitions? Okay, the Euler tour just gave us a list of these nodes. But what we want to do is also have some array of numbers where the LCA is going to be corresponding to the smallest number in a range. So we still don't see how to do that here. So the connection between them is going to be the following. We're going to define LV as the leftmost appearance of V in the array of the Euler tour. And RV is going to be the index of the rightmost appearance of V in the Euler tour. So at that point, we're beginning to connect things with numbers. So let's see this same tree that we had before. This was the Euler tour of the tree. And what we have written on top are the indices of the array of the Euler tour. So when we're saying, what's the leftmost index that we have in A? The leftmost index that we have in A is 1, because that's the leftmost place that we have in A. What's the rightmost? This should be an R, okay. So what's the rightmost index where we have an A? That's 19, because an A ends up here also. Okay, so let's move along. Then there's a B. What's the leftmost index for the B? That's a 2, because in the second position we have a B. And where is the B in the rightmost place? Well, that's the last B is this one, so that would be a 4. So the rightmost position of B is a 4. We move on to to C. C is the next letter. What's the leftmost place where we have a C? It's this index. And then the last time that we see a C is here in index 10, etc. So if we look for E, the leftmost is 3, and E doesn't really appear anywhere else, so that's also the rightmost position. So we have these left index and right index, and that we can do. We need to show that we can do this in linear time, and in fact we can, because the easiest way to do it is the one that you can actually assign in programming in the first programming class. The easiest way to do it is you scan A, you write all your, you prepare your table, L, V, and the A's, and then you start scanning from left to right, and every letter that you find, you write it down. If you see that there's already something written there, then obviously it was there before, so you don't write it down. This is going to fill in all the L's. And then you scan A from right to left, and you do the opposite. You write the first occurrence of each symbol as you see it on the right, and if you come to the same letter again, you don't write it anymore, because it means that someone was there before. So it's not the rightmost occurrence. So that's really very easy, but we're going to be a little bit more complex, because we want to learn something from this that will be useful to us. So, and this is the thing that's going to be extremely useful to us. So, we note the following. LV is where LV is equal to V, okay, because obviously that's the index in A where V occurred the leftmost time. Obviously, A of that index is equal to V. However, if we go to A of LV minus 1, if we go to the element that's to the left of LV, the level of that element is the level of V minus 1. Why? Because how did we get there? If this was the leftmost occurrence of V, Then how did we get there? We're getting there by the DFS. It's the very first time that we hit it when we're going by the DFS. And so how do we get to it? When the element before it, it's son, it's child. So therefore, the element before it, from which we arrived, has to have a level that is one less than us. So that would be with LV. Now, but every other situation of L, we're not coming from the top, we're actually coming from the bottom. Because again, we're doing a DFS. So, how do we... So, let's say that this is our node. We're in node A, node B, node C, node D, node E, and node F. Okay, so, and we're not concerned with node A. So the first time we get to it, we're coming down in the DFS, so we came from E. So in our Euler tour, the element just before the leftmost occurrence of A is going to be this E, and obviously it's a level above it. But then, what are all the other times that we get to A? We go down and we come up. So the other time, the element just before it in the Euler tour was below it. And then we go down and we come up. So again it was below it. And then we go down and we come up. So again it was below it. And finally, we go up again and that's it. At this point we finish this entire subtree in the Euler tour. So the leftmost is going to be the only situation in AV where the level of E, where the level of the element to the left of it was in fact less than it. In all the other cases, the level of the element next to it is going to be higher than it. What can we say though about the RV, or RA in this case? It's the opposite. The element after it, the only time when the element after the node that we're at has a lower level is going to be RV. So if we actually just go through the Euler tour, and we write down the level of every element in the Euler tour, then we can figure out the LV and the RV in one pass just by saying, okay, let's see, here's an element, the one before it was a level before, that's the L. The one after it was the level before, that's the R. Just by considering these two properties, we'll be able to find out who is the R and who is the L. Who is higher up? Lower level is closer to the root, I mean. Yes. Yes. Lower level is, the root is like level 0. This is actually something interesting because I started my life as a mathematician. And in mathematics, when they say a tree, so they draw the tree this way. So if you have a tree in mathematics, then this is how the tree is. And it kind of makes sense, right? Because most of us go out. I mean, I challenge you. Go out and you see. This is how a tree looks. Now, when we were a few months ago in Chennai, and there was a hurricane, there were 50,000 trees that were actually uprooted as a result of that storm. So the next day, you found a whole lot of trees looking like this. This is computer science trees. So mathematicians like to say that computer science is like a storm blowing through mathematics and upending everything. That's computer science. So the trees end up like that. And there's a interesting story in the Mishnah. So the Mishnah is the compendium of Jewish writings of the oral law it was actually written down about the year 150, which means we're talking about 1900 years ago, roughly, give or take. It was written down then, but it actually summarized Jewish knowledge of hundreds, if not 1,000 years before that. But it was oral. It was called the Oral Laws, and people just said it orally to each other. At that point, there were a number of reasons why they felt like it's necessary to write it down. Part of it is because the Romans were around and wreaking havoc, and there wasn't any central place to keep track of the oral law. And then things, since there wasn't a central place to keep the consistency, there started being already divergencies when people moved to different places and they taught things according to what they remembered orally, and then there started to be differences, so it was written down. And it was called the Mishnah. So in the Mishnah there's an interesting parable about 4 great rabbis who entered the orchard. Now the question is, what does an orchard mean? So the Kabbalah, I don't know if any of you heard about the Kabbalah, but the secret part of Judaism, the mystical part, is called the Kabbalah. And there are rules about who is allowed to study Kabbalah and who is not, and you can't study it unless you're at least 40 years old and you already know all the other branches of Judaism, etc., because it's otherwise it would cause to various difficulties. So this parable explains the difficulties. It says there were 4 great rabbis who entered the orchard. In other words, they studied this mystical part of Judaism. So Ben Azai, one of them was called Ben Azai, etzitz v'met. He looked in and he died. He couldn't take it, and he died as a result. Ben Zoma etzitz v'nifga. Ben Zoma was another great rabbi, and he looked into the orchard and he was stricken by it. In fact, there are stories that he had a mental breakdown. It's kind of what happened to Cantor when he looked at the mysticism of set theory. So he couldn't take it and he had a mental breakdown. Elisha ben Avuya was another one, kitzetz banetiyot. So that was a sad story because kitzetz banetiyot means he actually chopped down the trees. So the entire field is compared to an orchard. So he chopped down the trees. In other words, he became an apostate. He actually said, I don't believe in Judaism anymore. So it was tantamount to chopping down the trees. And Rabbi Akiva, who was one of the, if I need to write down who are the 5 greatest people in Jewish tradition in the 5,000-year history, Rabbi Akiva would be one of them. So they say Rabbi Akiva went in peace, then went out in peace. He went into the orchard, he studied, he did what he needed to do, and he went out. Everything was okay. He didn't die, he didn't become an apostate, he didn't become crazy. Everything was good. He was actually capable of doing it. Now, why am I telling you this story? Because of Elisha ben Avuya and the cutting off of the trees. So, as I told you, I was a mathematician. When I started studying, Bar Ilan University had a vision. They said, let's actually do a computer science, a math major, but a real math major. We're going to take people who really love mathematics and they're very good at it, and from day one we're going to have each one of them, from the first day that they enter undergraduate, we're going to assign a faculty member to give them reading materials and discuss with them, and they have a special course so that they are going to really do mathematics in depth from day one. And so they looked around and they tested and they asked for those who passed the test, they asked for volunteers, etc., and at the end, they ended up with 4 candidates, 4 people. So 4 people started that program. And so I was one of them, and Alex Lubotsky was also one of them. Alex Lubotsky, those of you who are mathematicians would know. He is one of the world-renowned mathematicians. He is at Hebrew University in Jerusalem. So Alex, he was involved, for example, the first explicit construction of expanders. So Alex Lubotsky was one of the co-authors there from the mathematics side. So he's really a world-renowned mathematician. Then there was another guy whose name was Moti Mushkin, and another guy, his name was Yigal Shendor. So these were the four. And looking back at it, it exactly matches the parable of the Mishnah. Because Moti Mushkin, although he studied mathematics, and he was really, all these guys were really, except me, all these other guys were really geniuses. So they were really, really good. And nevertheless, Moti Mushkin, when he finished his bachelor's degree, he went on and he got a PhD, but he went and he opened up a company and he had a couple of startups and he became a millionaire, and basically he went to the money side. So as far as mathematics is concerned, to go to the money side is like going mad. I mean, if you're a mathematician, you shouldn't look for money. So it's like he went mad. He went after the money instead of after math. Okay. Yigal Shendorf disappeared. I lost contact with him, and I never saw him for years. And then a couple of years ago, I was at a wedding, and they invited some real, in their sect, there are all kinds of sects of, there are rabbis who have like their disciples, and the groom was a disciple of some famous rabbi, and he invites his famous rabbi to give an exposition, a learned exposition, and he says Yigal Shendorf, and I said, well, that's not a very common name in Hebrew. It's not like, there are some names that are very common, and some names that are rare. The combination Yigal Shendorf is not a common name. So at the end, I grabbed him aside and I said, look, I went to school once in math with a guy named Yigal Shendorf. He says, oh yeah, that was me. So what happened? He finished a genius guy in mathematics, but then he became a great rabbi. So as far as math is concerned, he's dead to it. So here we have the guy who got mad. Here we have the guy because he got mad with money, like King Midas. And there we have the guy who died as far as math because he says, who cares? I mean, I have something else that I adore. And then there was me. Now I remained in academia and I do research and I prove theorems and everything else. But what do? My trees are upside down. So I'm the guy who uprooted the trees. And the only one who came in peace and went out in peace is Alex Lubotsky, because he became a professor of mathematics and did well for himself. So that's a case where the parable in the Mishnah of 1900 years ago fit exactly the situation that happened in real life to us. So yes, but so this is the depth. The depth starts at 0 here and goes down. But all the stories aside, so the key trait that we care about is the following. So we have an LV and we have an RV. But what do we have between them? So between them is exactly the Euler tour of the subtree that's rooted at V. So once you find the LV and the right V and the RV, everything between them in the Euler tour is precisely the subtree rooted at that. And that's an amazing trait, and already it comes and shows you how, in some sense, you'd be able to connect the range minimum query by height and the LCA. Because already this trait gives us the following conclusions. So what can we conclude? So if I tell you, well, pre-process something in linear time, and I'm going to ask you a bunch of questions. So what are we pre-processing in linear time? Doing the Euler tour and the LV and the RV, we can do all that in linear time. But now if I say to you, all right, my query is I give you a U and I give you a V, And I'm not asking for the lowest common ancestor, but I'm asking you, is U an ancestor of V or not? Not what is the lowest common ancestor of both, but is one of them an ancestor of the other? This in itself would be a question that would be a valid question to ask. I would assign it to you, let's say, as an exercise, and I would say, okay, write an algorithm that pre-processing is linear time, but then when I give you the two nodes, you tell me if one of them is an ancestor of the other. Well, we can do that because when would I know that U is an ancestor of V? If L of V, and in fact R of V as well, is between L of U and R of U. So that would make U an ancestor of V. And that is something that you can check in constant time, because go to the L array, find out what's LU, go to the R array, find out RU, go and look what's LV and check if this holds. Okay, you can also do something else. You can find out that U and V are unrelated at all. In other words, neither is an ancestor of the other if RU is less than LV or if RV is less than LU. So we can find this in constant time, and that's something that's in itself already we moved forward and we understand something. But now let's assume that U and V are unrelated. Okay, so, and let's also assume that RU is less than LV. And we can assume that without loss of generality. We'll just assume that the U is the one who comes before the V in the DFS. Now, LCA of UV is the vertex with the minimal level in the interval RU-LV. Let's look at the example. So here we have the U, here we have the V, and what did the Euler tour do? Once we came up, since U is to the left of V, so once we came up from U in the Euler tour, we're going to go and we'll follow whatever we follow, and then at some point we get to V. So what's the highest point that you can follow? The highest point between RU and LV is going to be this particular point, but that and it's going to be obviously by definition the LCA of UV. But that's the highest point that you can follow. So if we actually wrote down the levels of all the elements in the Euler tour and look at the array of levels in the Euler tour, so what you want when you want to find out what's the lowest common ancestor of U and V, what you want is the index of the smallest number between between RU and LV in the array. So there it is, there is the connection. So now you have you know how to find, assuming that you know how to find, to do range minimum queries, so you know how to find the LCA of these two elements. So here is our conclusion now. We're going to construct the array, the level array, level A1, level A2, up to level AN. We'll pre-process it for range minimum queries. And then we know that the LCA of UV is the range minimum of RULV in the level array. But, and this is a big but, okay, we don't really need a full-blown range minimum query for that. I mean, sure, range minimum query would work, but this is a special case of range minimum query. Why is it a special case? And we'll use that special case. We'll squeeze it to the max. Why is it a special case? Because it's a special case of the level array. And the level array is an array of the levels of the Euler tour. So what can you say? Can I have 5, 10, 13, 1? No. It's not going to look like that because this array has very small perturbations. every number is either plus 1 or minus 1 of the number next to it. There are no numbers that are really far from each other. And obviously, something like that should make life easier, and it will. So the important fact is that the range minimum queries are restricted in the sense that for any two adjacent numbers, level of AI and level of A plus 1, the difference is plus 1 or minus 1. And so it's not a huge range minimum query. It's a small range minimum query. Everything is happening like you climb, you go down, but the people next to you are all your own neighborhood. You're not going far. So where are we now? Okay. So where we are is the following. What we've managed to prove is twofold. One, we defined the range minimum problem. We saw that if we know how to do LCAs, we can take the range minimum, look at the Cartesian tree, do LCAs on that, and we can therefore, with preprocessing time, answer range minimum queries in constant time. And we showed the other side that if we knew how to do range minimum queries, then we can answer the LCA, because we're going to do the Euler tour, construct the R and the V, construct the level array, do range minimum on the level array, and that's going to give us the lowest common ancestor. So these problems help each other, and they help each other even, we don't even need the full-blown strength of one of them in one case, because it's restricted. So all we need to do now is to solve both of them. And so I'm going to define now the framework, but we're going to stop here for today and continue tomorrow. The framework is going to be the following. We're going to show a range minimum algorithm whose preprocessing time is not linear, but is almost linear. It's going to be O of n log n, and the query time is O of 1. So it's almost what we want, not exactly what we want. Then we're going to get rid of it. But within the description of this, we're going to use range minimum. Within the getting rid of the log n, we're going to use range minimum. And there's going to be a back and forth and give and take between special restricted cases of both problems until at the end we end up with both an LCA and a range minimum problem that has an O of n preprocessing and O of 1 query. So clearly, if I know how to do range minimum with O of n log n preprocessing and O of 1 query, then obviously we can also do an LCA with the same times, because because the reduction between one and the other was linear. So yes, we can do that. But we're going to end up with both of them being able to be done in time O of n. So get ready for the big ping pong tomorrow, and meanwhile enjoy the rest of the day.